Hi, this video is about momentum and impulse. Now, in our everyday language, momentum often is used in a way that it's not used in physics. It's often used in sports metaphors and so on. In fact, it often gets confused with the concept of inertia. But in physics, momentum is a vector quantity, and it encapsulates really three pieces of information about an object's motion: how much is moving, how fast it's moving, and where it's moving. So how much mass, what speed, and in what direction. So we define momentum as the product of mass and velocity. It's just m times v. And the symbol that we use for momentum is a lowercase p. Not a capital P, we use that for power and other things, but a lowercase p for momentum. I can't remember why. Anyway, simple example. If we have a bowling ball, 7-kilogram bowling ball, and it slides down the lane at, say, 16 meters per second north, we'll let north be positive. And the momentum of that bowling ball is just its mass times its velocity. So 7 times 16, which gives us 112. We might round that off to 110. And the units are kilograms, which is the unit of mass, times meters per second. So a kilogram meter per second is the unit of momentum. There's no special name for that unit in physics. We don't honor any other physicist by naming the unit of momentum after that person. So it's just kilograms times meters per second. Easy to remember because you can just look at the equation. If you want to change an object's momentum, though, you have to apply an impulse. Impulse is another thing that we define in physics. It's the product of force and time. And so the symbol that we use for impulse is a capital J. Again, I don't know why. But anyway, it's the product of F and T, so force times time. This is similar to how we define work as force times distance, but in this case it's force times time, and we call that quantity impulse. So if we push on an object, say with 28 newtons south, well, let south be negative, and we do so for a time of 4 seconds, then we'll produce an impulse that's equal to negative 28 times 4, which gives us an impulse of negative 112 newton seconds, which again we might round to 110, negative 110. And that's impulse. Oh, the unit. Yeah, force is measured in newtons and time in seconds. So the unit for impulse is just a newton second. A newton times a second. Sometimes the forces that we're dealing with won't be constant forces. So gravity is a fairly constant force, but imagine that you've got a tennis racket hitting a tennis ball. And so as that mesh of the racket gets pushed back, it stretches, and that produces a large force on the ball. And as the racket mesh de-stretches or unstretches, the force diminishes. So it starts off with almost no force on the ball, and then it hits and it increases rapidly as the mesh stretches. And then as the mesh relaxes, that force drops off. And so sometimes the force isn't constant, and we might need to calculate an impulse using, say, an average force. Or if we have a graph like this, it's really easy. Impulse is just force times time, which is equivalent to finding the area under that graph. So since the force is not constant, it depends on the stretch of the mesh on the racket, J, that is the impulse, can be found by determining the area under the curve on the force versus time graph. So if we could somehow calculate this area, we could determine what the impulse is. Another way to approach this is to try to look at the average force. If it's a pretty sharp spike like this, you can kind of determine the average force just kind of by eyeballing it. But otherwise, you might need to use more sophisticated techniques, some geometry and calculus. So we'll get to this thing in the next video as well, but just to introduce it here, it's called the impulse momentum theorem. And so, like I said, if you want to change an object's momentum, its speed or direction, you need to apply an impulse. And so notice first that the units for impulse and momentum are the same. So remember, for momentum, it was mass times velocity. That's a kilogram times a meter per second. And in impulse, it's a force times a time. That's a newton times a second. And those look different. But recall that a newton is really a kilogram times a meter per second squared. It's a mass times an acceleration, if you remember that from Newton's second law. So this newton is a kilogram times a meter per second squared, and then we're multiplying that newton by a second. And so when we multiply by the second, that second up here cancels one of the seconds in the bottom, over there, and we get a kilogram times a meter per second, which is the same as the unit for momentum. So if you want, and I actually prefer to do this because it's slightly shorter to write Newton seconds than it is to write kilogram meters per second. When you write units for momentum, you can write down kilogram meters per second. That's fine, that's A-okay. But you could also write down Newton
Miss
seconds.
Watkins, please call the front office.
That's the danger I get by filming these videos in the morning as the announcements come on. Anyway, those are the same thing. Now, back to this impulse momentum theorem. Impulse is equal to the change in momentum. Remember in energy we talked about how work equals the change in energy? Impulse equals the change in momentum in a very similar way. And you can write that a whole bunch of different ways. And so you should put one or all of these on your card. In addition to the box for momentum and the box for the impulse, this is the impulse momentum theorem, and I've written it a number of different ways. J, the impulse, is equal to delta P. That's the change in momentum. But remember, when we write delta P or change in something, it's always the final minus the initial. So I just wrote PF minus PI. Momentum is calculated times mass times velocity. So it's MVF minus MVI. That's the final momentum minus the initial momentum. And of course, if it's the same object, typically its mass isn't changing. At least it won't be for us. So I just factored the mass out. I said mass is times the change in velocity. And then, of course, in the last step, I indicated that impulse is calculated by looking at the force times the time. So all of these are useful in some problems and some in others. So you might want to put a bunch of them on your card, but at least put this one on there. That's the idea. The impulse equals the change in momentum. So if the initial momentum, say, of our bowling ball from before was positive 112 kilogram meters per second, and we applied an impulse southward at negative 112 Newton seconds, then what's the final momentum? So we could use this impulse equation. Final momentum minus initial momentum is the impulse. Plug in the values. And of course, if we start with 112 and we change it by negative 112, we're going to end up with zero momentum and zero velocity at the end. More on that on the next video.